Hello students, this is my second video on vectors. I'm trying to cover all the important topics with previous year questions. So watch till end. Now the unit vector n cap perpendicular to A and B is A cross B upon mod of A cross B. And a vector of magnitude lambda perpendicular to the plane of A and B is plus minus lambda A cross B upon mod of A cross B. Now here is the application. This question came in 2003 AIEEE exam. If U is equal to I plus J and V is equal to I minus J and W is equal to I plus 2J plus 3K, if n cap is a unit vector such that U dot n cap is equal to 0 and V dot n cap is equal to 0, then W dot n cap mod is equal to, since U dot n cap is equal to 0, dot product 0, V dot n cap is 0, again dot product is 0. If dot product is 0, that means n cap is perpendicular to U and n cap is perpendicular to V. So n cap is perpendicular to both U and V. And since we know the unit vector perpendicular to both U and V is U cross V upon mod of U cross V whole mod. Now cross product is I, J, K. So it's 1, 1, 0, 1, minus 1, 0. So when I solve this determinant, I get I cap 0 minus 0 minus J, 0 minus 0 plus K cap minus 1 minus 1. So this comes out to be minus of 2K cap. So that means U cross V is minus 2K cap and its modulus is 2. So the unit vector is n cap is U cross V upon mod of U cross V is minus 2K upon 2. So this is minus of K. And we have to find out the dot product of W with n cap. So my W vector, I have to find this. My W vector is here I cap plus 2J plus 3K. So, and its dot product with n cap is 0 into 1, 2 into 0 and minus 3. So, and its modulus is only 3. So my correct answer is here option A. Now next. Now this is what vector along the bisector of given two vectors. Now consider vectors A, AB, such is given to small a. AD vector is here B, forming a parallelogram ABCD. Consider two unit vectors along the given vectors which form a rhombus AB dash, C dash, D dash. So since AB dash is a unit vector, so this is A vector upon mod of A, and AD dash is again a unit vector, so this is B vector upon mod B. And using the parallelogram law of addition, we get AC dash is equal to AB dash plus AD dash. So here I have used parallelogram law of addition. So from there, what I get, AC dash is equal to AB dash plus BC dash, or AB dash plus AD dash. So since these are unit vectors, so AC dash is A vector upon mod A plus B vector upon mod B. So any vector along the bisector of bisector is, so any vector along the bisector is, since this is the bisector, so vector along the bisector is magnitude lambda A vector plus mod B plus B vector minus plus B vector upon mod B. Similarly, any vector along the external bisector, this is what the formula for internal bisector, and external bisector AC double dash, that is this, is lambda times A vector upon mod A minus B vector upon mod B. Rather you write here mu. So A vector upon mod A minus B vector upon mod B is what the external bisector, and internal bisector is a lambda times A vector upon mod A plus B vector upon mod B. So now here is the application of this. This question came on 7 January morning shift 2020 exam. Here A vector is given to us alpha I plus 2j plus beta k. Alpha beta both belongs to a set of real numbers. Lies in the plane of vector b I plus j and c I minus j plus 4k if A bisects the angle between B and C. So since we know that angle bisector between B vector and C vector, that is A given here, can be lambda unit vector B cap and C upon mod of C. This is what internal, or external is here mu B vector upon mod B minus C vector upon mod of C. Now, first of all, I am finding internal bisector. So here I write lambda, and B is here I plus j. So this is I plus j, and its mod is root of 2. And C vector is here given I minus j plus 4k. So this is I minus j plus 4k. And its mod is root 1 plus 1 plus 16, that is root of 18. And on further solving, I get this comes out to be 3 root 2. So now this A vector is here lambda times I plus j upon root 2 plus I minus j plus 4k upon 3 root 2. On further solving, I get this if I take 3 root 2 as LCM. So we get 3I plus 3j plus I minus j plus 4k. So this comes out to be lambda times lambda by 3 root 2, and here 3I plus I is 4I, 3j minus j is plus 2j plus 4k. Now this is what my internal bisector, and what else is given here, that A vector is this which lies in the plane of vectors these two. If A bisects the angle between B and C, that means this A is here my bisector. So internal bisector or maybe external bisector. So from the formula I derived this, and according to our quotient, this is given to us alpha I 2j plus beta k. So here I if compare the component of j here, j cap. So on comparing, what I get in this case, coefficient of j cap is 2. So I write here 2. Sorry, 2 upon 3 root 2. 2 lambda upon 3 root 2, and in this equation coefficient of j cap is 2, so my lambda comes out to be 3 root 2. Now if I put this value of lambda here, so my A vector comes out to be 3 root 2 by 3 root 2, so this is 4I plus 2j plus 4k. So my A vector is here 4I plus 2j plus 4k. So I just denote this by equation 2. This I obtained by using the formula of internal bisector. Now I'm using external bisector here. So for external bisector, if this A is what external bisector, so we write that B vector upon mod of B minus C vector upon mod of C. On further solving, I get this A is here mu times. So if I mu by 3 root 2 here, so what I get 3i plus 3j minus I plus j minus 4k. So what I get here, this is A mu upon 3 root 2, 3i minus I is 2i, 3j plus j is 4k minus 4k. Again, if I compare with the given equation of A, that is alpha I 2j plus beta k. So on comparing, what I get here, the coefficient of j, on comparing the coefficient of j cap, I get 4 mu 3 root 2 here, the coefficient of j cap, and in this equation that is 2. So my mu comes out to be 3 root 2 by 2. And if I put this in my equation 3, so my A vector comes out to be 3 root 2 by 2 into 3 root 2, 2i, 4, this is 4j, minus 4k. On further solving, my A vector comes out to be 2i plus 4j minus 4k divided by 2. So this was 4i, I think. So on further solving, I get this A as I 2j minus 2k. Now I denote this equation by 4. So here I have two equations. One is this, which I obtained by using the formula of external bisector, and the first one was this, which I obtained by using the formula of internal bisector. And now I have to put all these values, both values of internal bisector and external bisector, and check the option. So after checking, what I get that this external bisector will satisfy option C. That option is here. You have to check all the 4 options by both internal and external bisector. My option third was this. Option third was yes. So my option 3 was here, given to me. A dot k plus 2. Now my this external bisector is satisfying this equation. If I take dot product of A with k cap, so here I get this equation is satisfying. I dot j is 0, j dot k is 0, and k dot k is 1. So my answer is minus 2 plus 2. So this third option is satisfying the answer. So, and this is satisfied by external bisector. So my answer is here, option 3. Now here, it's very important again, scalar triple product. Let A, B, C be three vectors, then the scalar triple product, that is then this A cross B dot C is called the scalar triple product of A, B, C and is denoted by this. Then again I have written this A, B, C. This is how we denote scalar triple product, and this is equal to cross product of A cross B and then dot product with C. Further, here few properties are written here. Now this scalar triple product is obtained by just solving this determinant. This is what A, B, C scalar triple product. If my A vector is A1i, A1j plus A1i plus A2j plus A3k, B vector is B1i plus B2j plus B3k, and C vector is C1i plus E2j plus E3k, then scalar triple product is just solve this determinant A1, A2, A3, B1, B2, B3, and C1, C2, C3. So this is how we solve scalar triple product. These are few properties. Now I'm just rewriting this first property here. That is A, B, C. Just these are what the application of determinant, since scalar triple product is what determinant, solving the determinant. So A, B, C. If I move in clockwise sense, that means in this direction, this is equal to B, C, A. Further, again, if I move in this sense, clockwise direction, this is also equal to CAB. But if I flip these two terms, that means if I flip these two terms, then this comes out to be minus of ACB. This is what anti-clockwise movement. If I flip these two terms, then this is what minus of CBA, and if I flip these two terms, so this is equal to minus of BAC. So we are going to apply these properties in my coming problems. So ABC is equal to BCA is equal to CAB, but is equal to minus of ACB minus of CBA minus of BAC. Since this is what we obtain scalar triple product by solving determinant, therefore next property is here, A B will be 0 by, because if two rows are identical, then determinant is 0. Similarly, B, B, C or C, A, C, C. If two rows or two columns are identical, then we use the property of determinant. Then in that case, scalar triple product of AAA, BBC, ACC or CAC or anything ABA, if two rows are identical, then the value is here 0. Now, if we have to prove coplanarity, that means if A, B, C are coplanar, then in that case, scalar triple product is 0. So A, B, C is 0 if and only if they are coplanar. Again, here the property of determinant is written here. If I take scalar L, M, and N common, so we get L, M, N, A, B, C for scalars L, M, N. This is what again the property of determinant. Now here are the applications. Now in this question came on 2005, and the question written on right hand side came on 2019, 11 January exam. I'm solving the question which came on 2019. So you can try this question yourself. It's a simple one. Now, what is given here? If A vector is I plus 2j plus 4k, B vector is I plus lambda j plus 4k, and C vector is 2i plus 4j lambda square minus 1k be coplanar vectors, then the non-zero vector A cross C is. Now here, if these three vectors are coplanar, then determinant is 0. So A vector is here I plus 2j plus 4k. B is here I plus lambda j plus 4k. And C is here 2i plus 4j lambda square minus 1k. If these are coplanar, then scalar triple product is 0. That means this determinant 1, 2, 4, 1 lambda 4, 2, 4 lambda square minus 1 is 0. So from here, if I solve this is 1 into lambda square minus 1 minus 16 minus 2 lambda square minus 1 minus 8 plus 4 minus 2 lambda is equal to 0. On further solving, what I get, this is lambda cube minus lambda minus 16 minus 2 lambda square, and that is plus 18 plus 16 minus 8 lambda is equal to 0. These two gets cancelled out with each other, and we are left with lambda cube minus 2 lambda square minus 9 lambda minus 8 minus lambda minus 9 lambda plus 18 is equal to 0. This we can solve this easily, this cubic equation. Just take lambda common here, lambda square common here. Here I get lambda minus 2. If I take minus 9 common here, I get lambda minus 2. In next step, if I take lambda minus 2 common, I get lambda square minus 9 is equal to 0. And from here, what I get, lambda is equal to 2 and lambda is equal to plus minus 3. So we have three values of lambda. Now, if I put lambda is equal to 2, then A cross C comes out to be, this is I, J, K, and my A vector is given to be 1, 2, 4. So this is 1, 2, 4. And I am putting 2 in this C vector. So this is 2, 4. And if I put 2 here, this is 4 minus 1, 3. So 2, 4, 3. So I put here 2, 4, 3. And on solving, what I get, I 6 minus 16 minus j 3 minus 8 plus k 4 minus 4. So this is 10i plus 5j. But I have to check lambda plus minus 3 also. So in that case, from this I obtain this as my answer. But if I put lambda is equal to plus minus 3, then my A cross C comes out to be I, J, K, 1, 2, 4, 2, 4. And in place of lambda square, we get 9 minus 1. That is, if I put lambda is equal to plus minus 3, then lambda square is 9 for both the cases. So this comes out to be 8. And here I get 8. Now, as you can see, R2 and R3 are identical, are proportionate. So this is equal to 0. So my answer is 10i plus 5j, which is okay. My answer is here minus 10i. This minus 10i. 6 minus 16 is minus 10. So minus 10i plus 5j. So my correct option is here, option A. Now again, these are few properties on scalar triple product. As you know, we obtain scalar triple product by solving determinant. So I can rewrite this property as, this is what the sum of two determinant, those are A, B, C. That means I have taken the first term here of each A, B, C plus B, C, A. That is what the second term here, that is B, C, A. And as you know that A, B, C is equal to B, C, A using the clockwise sense. So this comes out to be 2abc. But in this second case, this can be written as, if I take all the first term using the properties of determinant a, b, c, so I can write this as a, b, c, and minus the second term, and those are here b, c, a. So my answer in this case is 0. So here is the application. Now this question came on 2000 entrance exam. Now, if ABC are unit coplanar vectors, then the scalar triple product of 2A, this we have to find out. And since ABC are unit coplanar vector, that means ABC are coplanar, then ABC scalar triple product is 0. And this we have to find. So using the properties, I can rewrite this as 2A, 2B, 2C minus BCA, and if I take 2 common from each row or each column, so here I get 8 common here. And since BCA is equal to ABC, and using the given condition that these three are coplanar using equation 1, so my answer is here 0. That means if ABC are coplanar, then this 2A minus B, 2B minus C, and 2C vector minus 2 is again coplanar. So my answer is here 0. Now another application. ABC are non-coplanar vectors and lambda is a real number. And here lambda A plus B, lambda square B, lambda C is equal to A, B plus B vector plus C vector and B vector. This is what the scalar triple product written on both the sides. So I'm just rewriting the given equation, that is lambda A plus B, lambda square B, lambda C, here A, B plus C and B. Now using my properties, I can rewrite as, first of all I take scalar lambda, lambda square and lambda common from here. So what I get, lambda to the power 4 here, and this turned out to be like this. Now using the property of determinant, I can write this as, if I take A, all this term A, B, C, so this comes out to be A, B, C and plus B, B, C. Same here, right hand side is A, B, B plus A, C, B. And if two rows are identical, then this is 0. Again here this is 0. So these two terms are 0. Now next lambda 4 A, B, C. And as we know that A, B, C is equal to minus of A, C, B. So that means ACB is equal to minus of ABC. On further solving, I get lambda 4 is equal to 1. So what we get, that it has no real values. Has no real values because lambda to the power 4 minus 1 gives us imaginary roots. So has no real roots. So my answer is here option B, that is exactly no value of lambda, as lambda is a real number given in the question. if A, B, C are three non-coplanar vectors and this capital A, capital B, capital C vectors are three vectors expressed in the terms of these A, B, C, that is A vector is capital A vector is x1A, y1B and z1C, B vector is x2A, y2B, z2C and C vector is x3A, y3B, z3C, then this the scalar triple product of A, B, C is x1, x2, x3, y1, y2, y3, z1, z2, z3 and the scalar triple product of these small a, small b, small c vectors. Those are non-coplanar. Now, using this concept, I can solve this question. A, B, C are non-coplanar vectors. That means these components are non-coplanar and lambda is a real number. Then the vectors these three. Then this vector A plus 2B plus 3C, comma lambda B plus 4C and 2 lambda minus 1C are non-coplanar. So here I am solving this using the method of contradiction. That means if I take these three as coplanar, here non-coplanar is given, but I am using this, I am just solving this question using the method of contradiction. If I take these three are coplanar, then determinant 1, 2, 3, lambda, this is 0, lambda 4, 0, 0, 2 lambda minus 1 is 0 here. Now if I expand along C1, so what I get, lambda 2 lambda minus 1 is equal to 0. So from here we get two values of lambda, that is lambda is equal to 0 and lambda is equal to 1 by 2. So what we get, that if lambda is equal to 0 and lambda is equal to 1 by 2, then these three vectors are coplanar. So my answer is that except these two values, that is lambda 0 and lambda 1 by 2, these three are non-coplanar. So my answer is option C, all except two values of lambda, and those two values are lambda is equal to 0 and lambda is equal to 1 by 2. So correct option is here option C, all except two values of lambda. This question came on 2004 AIEEE exam. So this is all about today's video. I will catch you guys very soon with remaining topics of vector. Please like and share the video with people around you and subscribe my channel method wise. Thank you.